How many states does it have?
Oh, I think it has
Well, I'm not asking you what you think. I want you to look at it and tell me what it has, how many it has.
it has 2 states, I think.
And how many does the DFA for that have?
2.
Then they're already screwed up. It's
Oh,
3.
sorry. I guess I screwed up. Thank you for
Yes.
telling me.
Sorry about. Both DFAs for A star and for B star have 3 states, and so the complementation, of course, then has 3 states. Then you do the concatenation. These are again. You have 3 plus 3, so this is 5 states because the initial state is the same. And so then you have to make that deterministic, and then you can flip the states for the last complementation, and then you can do the reduction. Okay, but if your DFA already is wrong, then there's not a whole lot we can give you.
Oh, I see. Thank you for telling me.
Okay.
I hope I can do better. I hope I could do better on the question based on the reduced DFA on the final.
Well, I hope so too. I don't particularly take any joy in giving bad grades to people. It's much
Okay.
easier. It's much easier if everybody earned an A.
Okay.
Any other questions?
I have a quick question about question 4 on the exam as well, which is constructing a Chomsky normal form.
Yes.
For the grammar. I know it's a lot of writing. Would you be able to maybe just quickly go over the final, the final Chomsky normal form for the grammar, or for the language of the grammar, so I can possibly compare what I have to understand maybe why I lost some points on it?
Well, there are different ways of going about it, all of which are correct. But basically, what you're going to have is something. Where are we? Let's see, we have this. Maybe copy that there. All right, so we have, you do S goes to B, X, D, S, X, A, S, X, A, S, and then B, S, S, and B, let's just stick to that. So that S, then this gives you S goes to B, S1, and S1 goes to XA, S2, and then S2 goes to S, S3, and then S3 goes to XA, S4, and S4 goes to S, S5, and S5 then goes to XA, S. So that gets you this, and then you have S goes to BS6, and S6 goes to SS, and then you have B, which is that. So you replace the S productions by all that, and you have XA goes to A, and that is it for B. S goes to something, and then you do the same thing for the B's. Okay?
Wouldn't you have to remove the unit production B goes to S first?
Yeah.
Right. So basically you would get that first, and
Right.
S goes to
That's
BXD.
why I only did this one. I mean, the
right.
unit...
You'd basically do this almost the same thing, except for B goes.
Exactly.
You would start with S.
Exactly.
Okay. Okay. So I basically got that exact same answer, but I actually, I don't know why I said basically, I got that exact same answer, but I lost 10 out of the 15 points, so I should probably reach out to the TA maybe to understand more.
Yes, right.
Okay.
If it's very similar to what I have there, then there may be a little problem. Okay?
Okay, thank you.
Any other questions?
Professor, so we have the net exam in next week, right?
Yes, on Wednesday.
Oh, thank you, sir.
Any other questions?
Can we know about the average of the exam too?
I have no interest in advertising averages. You are not competing against anybody except yourself. Okay, no.
Professor, oh, sorry.
Yes, go ahead.
Can you go over question 2 from the exercise set 3? Like maybe one question?
Question 2, exercise 3. Okay. Let's see. Where are we? But I did one already last time, didn't I?
Maybe I wasn't here. Sorry then.
Well, then you better find out what you missed, because I don't really like to repeat what I've done already.
All right. Thank you so much.
Okay, but what I did last time was the 2A, and basically what you do is you non-deterministically go to a state in which the first half of that is being accepted, or you go to a state where the second half of that is accepted. So the first half is, of course, something we've already done. The second half, you basically have to, well, one possibility is to, and that's a little different from what I showed you last time, so there are two possibilities. You could, for instance, put for every 0 that you see, now we're looking at 0 to the I, 1 to the 2I. For every 0 that you see, you put 2 markers on the stack. Okay, you can do that in one step. And then for every 1 that you see, you need to remove a marker for a 0. So that way you are going to get twice as many 1s as you get 0s. And the other 3 questions, you just have to find out what is the language that is generated by these grammars. That's not very complicated. Okay? Other questions?
So is our final answer for the PDFs, will it be a state graph, or will it be like our NFA and DFAs with a table with numbers in it?
There is no state graph. You need to have a table. Basically, it's the move function. The move function that you need to indicate. Where are we? The move function that where you have a state and then you have the various stack symbols, and then you have the symbols from input, and then for each of those entries you have to write down what it is. Okay?
All right, thanks.
Any other questions? Okay, so today the program is the following. Given a push-down automaton, P, which consists of states, input symbols, stack symbols, the move function, the initial state, the initial stack symbol, and no final states, because we're looking at accepting by empty stack. Obviously, if we accept by empty stack, the set of final states can be empty. So, given a PDA, construct a context-free grammar G such that the language generated by that grammar G is the language accepted by the push-down automaton by empty stack. Okay. So this G is going to be a set of variables, those terminals T, a set of productions, and a starting symbol. And so the first issue is what is N? N is the symbol S and triples consisting of a state, a stack symbol, and another state. So this is our N. We have N. T, of course, is known. S is simply a starting symbol. So the only thing, in quotes, that we need to specify is P. So there are two rules. The first one is a simple rule. We have S goes to Q0, Z0, and Q for all Q in capital Q. So what is important here is that this Q0 is that Q0. This Z0 is that Z0. So what we have basically in this case is a free variable for all Q in capital Q. So if we have M states, we have M productions. The Q0 is fixed, the Z0 is fixed, and the Q is a free variable. And that will be useful in what follows, because in all these rules, which is essentially a pattern matching exercise, you have to identify what are the free variables and what are the bound variables. So if Q1, B1, B2, Bm is in delta Q little a and capital A. So in this case, we obviously have Q1 and Q are variables, are states. Capital A, B1 through Bm are stack symbols, and A is either a terminal input symbol or epsilon. So if that's the case, then we have the production Q, capital A, P, goes to little a, Q1, B1, Q2, B2, Q3, and so on, QM, BM, QM plus 1, where P is equal to QM plus 1. So this P is that QM. I'm sorry, I didn't write that properly. This is Q gamma. B1, Q2, Q2, B2, Q3. So this is the same. The Q3 follows that, and then you have the QM. So this is basically a chain. And the P that we have here is equal to that QM plus 1. So 3 variables here are the Q2 through QM. Because the Q2 and the Q3 and the QM are all states, but they're free, whereas the this Q1 is not free because this is that. And that Q is this. And obviously the A is this, and the little a is that, and the B1 through Bm are all these. So the free variables here are Q2 through Qm. Actually, Qm plus 1. Because the P is free, which is equal to Qm plus 1, but it is written down here. So depending on how you want to state that. So what you have then is the Q, which is that Q, the capital A, which is that capital A, the P, which is equal to the Qm plus 1, which is free, so it ranges over all states. So when I say free variable, I basically mean that it ranges over all states.
Professor, I have a question.
Yes.
Okay, so I want to know what the relationship is of this of the PQM plus one, right? So that would be everything that is not being looked at right now, correct?
I don't follow.
So if we're looking at, because what does the P relate to in the actual equation? Is it the stack?
No, no. The P, look, the variables are triples consisting of a state, a stack symbol, and a state. So this triple is a single variable, which is part of that grammar. And so basically this is a variable, QAP produces little a followed by this variable, that variable, M variables. So these are grammar variables. Q1, B1, Q2 is a grammar variable. Q2, B3, Q3 is a grammar variable, and so on and so forth. So what that means is that since these are free variables, Q2 through Qm plus 1, and if we say we have n states in Q, then there will be n possible P's, and for each of the free variables Q2 through Qm, there are going to be n possibilities, so there are n to the mth different productions for each specific P. So since there are n P's, there will be m to the n plus first productions. M to the n productions for each of these possible P's, of which there are n. Okay?
Yes. So how do we, at what point do we determine whether or not it's an accepting or not accepting state if there's n plus 1 to look through?
You have to write them all down.
Okay.
Every one of them is a possible production. And of course, we don't have any states that accept because this is acceptance by empty stack. So that's the grammar basically will generate strings, and of course one would hope that there are some that don't have any variables, Q1, B1, Q2, and so on and so forth, because then you're just left with the A. If you don't have any productions where there is no variable on the right-hand side, then obviously your grammar is not generating anything. So that would have to be.
So
All right, so a special case.
Just to make sure to close that part up, does that mean that if any one of these states is actually not a state, like it does rejecting, the whole thing is rejecting?
Look, you're confusing things seriously. A grammar does not reject anything. A grammar generates something.
Okay.
Okay, so the grammar, this is a production where this variable generates this right-hand side. So this variable, QAP, can be replaced by the whole right-hand side, which is little a followed by m different variables. First one is Q1, B1, Q2. The second one is Q2, B2, Q3. Down to the mth one, which is Qm, Bm, Qm plus 1. And that Qm plus 1 has to be equal to that P here.
Okay, so this is more of like making a grammar rather than actually.
Yes, that's what we're defining. I mean, we've defined the variables, the S is given, the terminals are given, and so what we're doing now is the productions. And so we have these productions. S goes to something that starts off things, and then rule number 2, if this is a entry in the move function for QA and capital A, then this whole slew of productions is generated by that.
Okay, thank you. Now I understand.
And so if M is equal to 0, then we have a special case. Then that means Q1 is P, because we don't get any further. And we have P epsilon in delta of Q little a and capital A. And so then the production is Q capital A P goes to little a. So this is a special case. All right, so let's look at an example. This needs to be carried out. And so let's look at the following push-down automaton. We have Q, we have Z, and we have X. And we have 0, 1, and epsilon. And then we have a second state Q1. And of course we have Z and X, the stack symbols again. And now here are our entries. If we are in Q0 and we see Z on top of the stack, and we read a 0, then we put X on top of that Z. In all other cases in this row, we have nothing. In the case that we see X on top of the stack, we put another marker on top of the X, so this X is replaced by XX. And so that will be, if we see 0, if we read 0, and if we read 1, then we basically eliminate that marker using that 1 and go to state Q1. We don't want to see any 0 once we're in state Q1, so this is all no good. We don't want to see Z on top of the stack when we have a 1 to read, but if we see an X, we stay in Q1 and we eliminate the marker. And then we have two other cases. We have Q1 epsilon. If we expose the Z on top of the stack and read epsilon, and similarly, if we see an X on top of the stack, we can read nothing, epsilon, and remove that X. So now this is a fairly simple push-down automaton. And so we will have to see how that works. So let's look at the first case where we have delta of Q0, Z, and 0 contains Q0, X, Z. So we have Q0, X, Z is contained in delta of Q0, Z, and 0. Okay. So this is now a pattern matching exercise. So let me just copy that. And stick it in here. Oh, come on. All right, no good. Move that stuff down. No, 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 forget it. All right, I'll just write it down. This is Q0 and X, Z is in delta of Q0, Z, and 0. So this is what I'm going to work on. So what we need to do then is, obviously we first have from rule 1, so this is, of course, we have S goes to R. So the initial state is Q0, and we have Z, and we have Q0, and we have also S goes to Q0, Z, and Q1. So this is according to the rule number 1. That's sort of trivial, but we have to get this whole thing started. Since we have this Q being a free variable, it has to range over all states. So that means in this particular case, in our push-down automaton, we have two states, Q0 and Q1. So that means we're going to get two productions. S goes to Q0, Z, Q0, and S goes to Q0, Z, Q1, because that Q that we have here ranges over all states. There are two states, Q0 and Q1. This is the free variable. The other two components of that triple are, of course, fixed. Q0 stays, Z0 is the initial stack symbol, stays. This is Z in our case. And so that's the stuff we get according to rule 1. So this is nothing particularly challenging. So now we're going to do rule 2 for, well, basically each of these entries. We have this entry, we have this entry, we have this entry, we have this entry, and that entry. So there are 1, 2, 3, 4, 5, 6 entries in the move function, each of which will give us a number of productions. Now, if you look at this rule 2, basically what happens is the key point is that M, B1 through Bm. So that means we have 2 here, we have 2 here, we have 0 here, 0 here, 0 here, and 0 here. Okay? So this M that we're looking at in rule 2, that M is given by the length of the string over the stack symbols that are in each of those entries. So xz, which is the one we're now looking at, this is m is equal to 2. And so we can immediately say how many productions we're going to get. Okay, we have P ranges over Q0 and Q1. This is the same deal that we have here. And then we have free variables Q2 and Q3. So that means we altogether get, because we have two states in Q, we're going to get exactly 4 productions for this. So according to the first step, we have Q, A, P. So the Q, so this is where the pattern matching occurs. That Q is this Q, which is that Q0 that we have here. So we have Q0. Then we have this capital A. That capital A, well, all right. I wrote this backwards, so let's do 0 and Z. Zero and C. So what we have then is that Z is that A here. And the little a is the 0. So that means when we do this, we have the A. This is that A. So that is Z. That is our Z here. This Z is that A because it is that A. Delta of Q, little a, capital A, delta Q0, 0, Z. So you have to match this up so that the capital A is the capital Z and the little a is that 0. Okay, and so now that P is free. And so we generate here, according to that little a, well, that little a is 0. Okay, and then we have B1 and B2. So you can immediately do this. And leave those places open. So this is going to be that. And that is a free variable. And this is going to be that. And that is a free variable. And now that Q1, what is the Q1? The Q1 is this. So that is the Q0 here. So we have to do that matching up. This Q1, B1 through Bm is Q0xz. So this is the Q0 that we have from that. And the rest are free variables. So the P, which is the Q3, which is the same, is fixed, is ranges over all variables. So it can be Q0, it can be Q1. And then the Q2, again, ranges over all variables. So it can be Q0 or Q1. So what you have then is something here and something here. And so these have to range over the two variables that we have in this case. And so the final result then is going to be that we're going to get these 4 productions. So I'm going to replace this thing by Q0, and that gives me Q0, that is fixed, B1, and there is stuff that is to be filled in, B2 and Q0. Okay, so now we have to work on the other possibilities, of course, where we replace this circle by Q1. The other possibility, because we have only two states, so this is then going to give us the same thing, Q0, B1, and the asterisk will still have to be replaced by something. And so this is now Q1 because this is that. So that has to be the same as this. So that's why the Q0 here is that Q0 here. And that Q1 here is that Q1 here. And now we have to do this asterisk, if you will. And that has to range over Q0 and Q1. So if we stick in Q0, they have to be, of course, the same. Then we need the other possibilities, Z0, Q0, B1, and Q1. And then we have Q1, B2, and Q0. And now, of course, I wrote down the Q0, the B1 through B2, but that's, of course, not what it is. It is X and Z. So this is X, and this is Z. Remember, this is B1 through B2. That's the X and Z. So we're doing this. And so the same thing for here. X and Z, and the same thing here, X and Z. And now we again have to rattle through the possibilities for that circle, so Q0, Q0, or 0, Q0, X, Q1, and Q1, Z, Q1. And so this now is the final answer, those 4 productions that we get from this.
What question is this asking? I'm looking at it, but if I just saw this, I wouldn't know what it would be asking. Is it
given a push-down automaton that accepts by empty stack, construct a context-free grammar such that the language that this grammar accepts, that this grammar generates, is exactly the language that the push-down automaton accepts by empty stack.
So it would say all of that, and then it would show this like this thing that you circled, and then from there on.
No, this is given.
Mm-hmm.
This is given. This is this. Delta of Q0 and Z0 and Z contains Q0XZ. That's what that is. Okay, so this is this. And from that, we are going to get these 4 productions. 1, 2, 3, 4. And the 4 is because we have 2, the M is 2, and the number of states is 2, so we get 2 to the power of 2, which is 4 productions from that. Then the next thing that you're going to get is from this. You're also going to get 4 productions from that. Okay, so let's look at that. Q0 XX is in delta of Q0, 0, and X. So now we have to go back and forth. Basically, we have to get, we have to apply this rule 2. So we have Q1, B1, B2 through Bm. So this is Q1. That Q1 is that. So we have Q, this is that Q, and that A, and then P. So let me see, how am I going to screw this up? Basically, we now have to do that pattern matching process. So that, let me do it blue maybe. So this is our little a. Then we have our capital A. This is our capital A. And this is Q. And then we have Q1, B1, B2. So this is the situation that we're looking at. And so in that case, we have Q, A, P, where that is that Q, that capital A, and the P, as I said, is a free variable, so we get little a, which is that little a, and then we have Q1, which is that Q1, and then B1, Q2, the Q2 is free, Q2, B2, Q3, and so that P is that, and that is this. And so in that case, we then have to do the matching. So the productions that we're
sorry, can I interrupt you? How do you know when a variable is free?
I said that when it doesn't, all right, go back to that. A variable is free if it is not bound. So in rule 1, Q0 and Z0 are both bound and Q is free. In rule number 2, Q0 is fixed. I'm sorry, Q1 is fixed. B1 through Bm are fixed. Q is fixed. Little a and capital A are both fixed. So whatever else is left is free. So that Q is that Q. So that's bound. That capital A is that capital A. That's bound. That P is not bound. It is free. Now, it has to be equal to that last state here, but P is equal to Qm plus 1. but that is a free variable. And then you have little a, which is of course bound. Q1 is bound because this is that Q1 here. And then B1 is bound, B2 is bound. Q2, on the other hand, is free, and Q3 and so on is free. Of course, in this case, we have only m is equal to 2, which means we have only Q2, which is this situation. We have that Q2, and we have that Q3, which is equal to P. So these two, this one is a free variable, and this is a free variable. Everything else is fixed. So what that means is we're going to get that Q, which is Q. Why does it write things? So we have this Q is Q0. That's that Q0. And then we have capital A is X. And then the P is free variable. Then we have little a, which is 0. Then we have Q1, which is that Q0. If you look at that, this is that matching up, Q0. And then we rattle through B1 and B2, so this is X and X again, and then that. So now we have this free and that free. And so we rattle through all the possibilities for the two free variables. So that gives us Q0, X, Q0. That's replacing this by Q0, which means I'm going to have Q0 here as well. And then I have 0, Q0, this is fixed, X, and Q0, Q0, X, and Q0. So that means I'm replacing these two by Q0, or I'm replacing them by 1, Q1, Q0. This is X, Q1, Q1, X, Q0. This is, of course, this Q0. And then I have to do exactly the same thing, except now I'm replacing this by Q1. So this is Q1. I get all that. So I get here Q1 and I get here Q1. And everything else is basically the same. So 0, Q0, X, Q0. And Q0, X, Q1, or 0, Q0, X, Q1, Q1, X, Q1. So that entry Q0XX is going to give us those four productions. Okay, and then we look at this. So we have Q0, Q1 epsilon is in the move function of Q0 and 1 and X. So this is that. Q1 epsilon is in Q's delta of Q0, 1 and X. That's what that is. And in this case, we're looking at the special case. In this case, we have Q1, that Q1 is P, so we're going to get exactly a single production because, well, we have two states, and so 2 to the power of 0 is 1. So we get that Q0, that Q1, which is our Q1, is going to give us 1. So we have Q1, and we have X, and we have Q0. If we look at that, if you match this up, then you have here P, that's that P is going to be the Q1, which is that. So that is the Q1. Let's see, where are we? So Q1 is P. Q and P. I'm sorry, this should be Q1. So we get Q1, X, Q1 goes to 1. This is our little a. So if we look at that matching up again, the Q1, that's the P, so that is that, and this is our A, and this is our little a, and then Q, this is our Q, which is Q1. So we get this production from that, and you can easily see by applying the same rule, you're going to get the same thing from these three. So you get altogether 1, 2, 3 more productions. Take that one, so that's 4, plus 4 for this, plus 4 for this. So altogether you have 12 productions from rule number 2, plus 2 productions from rule number 1. So you have 12 productions from rule 2, plus 2 productions from rule 1. Ultimately, the fundamental question is you have to do the pattern matching, you have to determine what are the free variables, and then basically enumerate all possibilities. So if you have M, so B1 through Bm, and you have N states, then you have basically N to the power of M productions from one entry. Okay? So in this particular case, we have an entry here for M is 2. So that's because we have 2 states, we have 2 to the power of 2 productions for that entry. Then we have the same number of productions for this entry because it has, again, 2 stack symbols in that entry, and you have 2 states. So this is, again, 2 to the power of 2, 4. Then you have 2 to the power of zeros, which is 1 for this, and 1 for this, and 1 for this, and 1 for this. So this is where you get those 12 productions, 4 plus 4 plus 1 plus 1 plus 1 plus 1 plus 1. It's 12 plus the 2 productions from rule 1. And that basically then gives you the final result that then gives you a context-free grammar. We've now completed the set of productions, and I'm going to spare you the proof. Basically, the proof that this grammar actually generates everything that the push-down automaton accepts by empty stack is that you basically get, if you take a leftmost derivation in that grammar, then it basically simulates what is being manipulated on the stack of the push-down automaton. And that means, of course, eventually the stack of the push-down automaton is empty, and that means the grammar generates a word that doesn't contain any variables. And so in that case, you are going to get a corresponding string. So that is, as I hinted, definitely the ugliest construction that we have in this course. What is important is to keep in mind that what you now know, okay, we know that anything, any language accepted by a push-down automaton can be generated by some context-free grammar. So that is what this construction is all about. And of course, it is a slightly more general statement, any language accepted by a push-down automaton. Well, if that push-down automaton were to accept by final state, then we first have to throw the construction, convert the NFA from acceptance by final state to acceptance by empty stack. And now that push-down automaton that we get, that accepts by empty stack, that is then the push-down automaton to which we apply this construction of a context-free grammar. And so that context-free grammar then will accept that language, that will generate the language that this push-down automaton accepts. And of course, the converse is also true. Any language generated by a context-free grammar can be accepted by some push-down automaton. This, of course, is where we start with the context-free grammar, convert it into Greiberg normal form, and then apply the construction we did a week ago, which gives us a push-down automaton with a single state that accepts by empty stack precisely the language that this grammar in Greibach normal form generates. So that means now if we have the languages, class of languages accepted by push-down automata, and the class of languages accepted by context-free generated by context-free grammars, that happens to be exactly the same class of languages. So whatever you can do with a push-down automaton, you can do with a context-free grammar, and whatever you can do with a context-free grammar, you can do with a push-down automaton. So that means that context-free grammars and push-down automata are equivalent as far as their power of defining a language is concerned. And that's all I really was planning to do today. Now, what we're still missing is, of course, a device to accept non-context-free languages. So we have already established that a to the n, b to the n, c to the n, n greater or equal to 1 is not context-free. Which means, of course, given the equivalence of push-down automata in context-free grammars, it means that there can't be a push-down automaton and there can't be a context-free grammar for this language, a to the n, b to the n, c to the n. So the way we're going to deal with that question is we're going to define a Turing machine. I'm not going to go into detail today. I'm just giving you a preview and relate that to push-down automata. If you recall, we looked first at finite automata, which essentially didn't have any separate storage facility. So if you wanted to store some information, it would have to be stored in the state. In other words, being in a particular state will provide some information, but it certainly, because there's a finite number of states in a finite automaton, it will give you a finite amount of information that can be conveyed using the location information state, basically. So what we then did was extended that to push-down automata, where we essentially added a storage device, an unrestricted, unlimited storage device, which was a stack. But as you see, this language is not accepted by a push-down automaton, and therefore that stack that you have to store information is insufficient to deal with this language. The same thing with WW, WA star, A01 star, or if you want to put a 2 in there. We talked about that last time. So these are all not accepted by push-down automata and therefore also not generated by context-free grammar. So what a Turing machine does is basically it has a tape and a finite automaton with a read-write head. And this tape consists of cells, and the read-write head basically can read what is in a cell, change the content of that cell, and then move either to the left or to the right of the cell that it has looked at. So this is one move. Determine what state you're in the finite automaton, read the content of the cell that the read-write head is looking at, and on the basis of that state and content of that cell, change the content of that cell, change the state, and move either to the left or to the right of the cell, which then allows you to start the whole process again. You are now in a state, you see the content of a cell, and on the basis of that, you can then make another move, and so on and so forth. And that basically allows us to deal with more complicated languages, for instance, this one. Now, Turing machines are not particularly smart and not particularly efficient. How would a Turing machine deal with a to the n, b to the n, c to the n? Well, the Turing machine will basically start with an a little a, and mark it. And then it will move to the right until it finds a little b and mark it. And then it keeps on moving, finding a little c and mark it. So at this point, it has basically found an a and a corresponding b and a corresponding c and marked them off. And then it moves back to find the next little a, and it marks that little a off, throws for another little b, marks that one off, throws for a little c, and marks that one off, and so on and so forth. So in this way, it always finds matching a, b, and c instances. And if in the end everything is used up, everything is marked, then the word is a to the n, b to the n, c to the n for some n. If, on the other hand, it doesn't find an a, but it still has b's and c's, then obviously this is no good. Or if there are too many b's but not enough a's or c's. So there are various ways in which this can fail. And we will talk about this more formally, but you can easily see the Turing machine can go back and forth many, many times, not terribly efficiently. So it really doesn't count in the sense of counting 1, 2, 3, 4, 5, 6, 7. So it doesn't really say, oh, well, there are 343 A's followed by 343 B's followed by 343 C's, and that is a word in the language. It basically says there's an A with a corresponding B and a corresponding C, and then I keep repeating it. And if I eventually run out of all A's, B's, and C's at the same time, then that word is okay. If not, the word is not okay. We'll talk in more detail and with more precision about that on Wednesday. Any questions?
Could we go over the PowerPoint one by one, please?
Absolutely. No problem. Okay. Number 1. Number 2. Number 3. Number 4. And number 5.
I have a question on the earlier question that we actually were trying to answer, the Q0, Q1 question. Is that enough to actually demonstrate that the all languages of PDA is equal to the language of context free? Would that be like a proof?
Well, what I didn't prove formally was that if you have a word that is accepted by empty stack, by the push-down automaton, then that word is also generated by the context-free grammar that we constructed here. But you can show that. The textbook contains it if you really want to spend 3 or 4 hours.
And then my last question is on the Turing machine. This is not a stack at all, right?
No.
Tape.
This is a tape, and it can mess with anything. If it changes the content of this cell and moves to the left, it can change that content of that cell, and then it can move to the right, and so on and so forth. It can do whatever it wants. There is no restriction on the way in which the read-write head can move around. Yes, otherwise you would have a stack, and we've already established that that is certainly not going to be used for A to the N, B to the N, C to the N, for non-context-free languages.
Does a Turing machine create anything? You know how like a PDA would create a grammar?
Well, you create the grammar. The push-down, the Turing machine doesn't really. There are grammars, but they're so complicated that it is probably much easier to just think of the Turing machine. There are so-called type 0 grammars, which allow certain things, but nobody really studies those.
Not yet.
No, we won't. Don't worry. But if you want to, yep, they're type 0. They're called type 0 grammars. And they correspond to Turing machines, but in a complicated way. Not nearly as straightforward as push-down automata and context-free grammars. Any other questions?
Will Turing machines be on the test?
Yes. They're on the exercise sheet number 3. So, as I have indicated, all the questions on the exercise sets are tied very directly to the various. The exercise set I corresponds to the exam I equal to 1, 2, 3. Any other questions? All right, then we will talk on Wednesday in more detail about Turing machines. Bye-bye. Have a good evening.